Oh, yes. Let's go
Good call.
live. Before we get started and we introduce Carina, here's Vivian White with some announcements.
Hey everyone. It's so good to see so many people joining us tonight. Thanks
Oh,
to
yes.
Kat, who is
Let's go
hosting.
live.
Oh, that's right. I'm just gonna
So
nudge. There we go. There you are again. Thanks to Kat, who's hosting for the first time this evening on our very own. We appreciate you bearing with us as we work this all out. Brian will be joining us again, taking a little break, working on a different project. So, a couple of quick things. We have been having some issues with having photos uploaded. Thank you so much for everyone who told us about that and helped us work it all out. We think it's working again. If you have any trouble with photos, just shoot us an email at nightskyinfo@astrosociety.org. And Kat has got some office hours coming up. And for Night Sky Network members, if you're interested in getting your club going again on the Night Sky Network, or you have any questions for us, I'll stick that link in the chat, which I believe you'll be able to see. Give me 1 second. I want to also encourage everyone to please sign up for Eclipse Ambassadors. If you had any fun at all at the last eclipse, and even if you didn't and you love eclipses, go ahead and join us. Eclipse Ambassadors, we're partnering eclipse enthusiasts and amateur astronomers with undergraduates, and we're getting you prepared to get your community prepared before the eclipse. So there's nothing that you have to do on the eclipse. We're just getting everybody ready because we know that many of us will not be in our hometown for the eclipse. A lot of us are going to go to the path. So join us in Eclipse Ambassadors. It's a super easy sign up and a lot of fun, and you get lots of glasses and swag. Right. I think that's it for me, Kat.
all right, thank you. For those of you on Zoom, we do apologize about the chat issue. If you want, you can just use the Q&A window to chat with everyone else and to ask the speaker questions. Traditionally, we would have them separate, but today we're just going to use the Q&A window. But if you are having any additional technical issues, like Vivian mentioned, you can go ahead and email us at nightskyinfo@astrosociety.org. And so today we have Carina Alden for our webinar. Carina Alden is a space weather analyst with the Moon to Mars Space Weather Analysis Office at NASA's Goddard Space Flight Center. She stares safely at the sun all day, monitoring solar activity and any impacts our sun may have across the solar system in support of NASA deep space human and robotic missions. Carina says that being her authentic self is learning how to follow what excites her, and that has helped her on her journey to become a space weather analyst. So, Carina, with no ado, further, take it away.
Thanks, Kat. Alrighty, I'm gonna start sharing my screen. No peeking. Alrighty. Hope everybody can see that. Please feel free. Oh, I got ahead. I already got the sneak peek. Alrighty. So, I'm going to talk a little bit about what life is like as a space weather analyst. And so, before I do that, I thought it would be kind of important to talk about what space weather is. And so, what is space weather? So, if you Google what space weather is, you look up the definition, you'll probably come across multiple definitions that all point to something about the sun and its relation to Earth. However, space weather stretches beyond Earth and into the interplanetary space. And so impacts can go to missions and other planets all throughout our solar system. And so, space weather, by definition, is the relation of the sun's activity to interplanetary space and all its inhabitants, but also how those inhabitants feed back into the activity in space. So, what do I mean by that? Well, space weather, by most folks' definition, starts with our closest star, the sun. But if you ask the ITM community, so the ionosphere community, they'd tell you otherwise, and they'd let you know that there is stuff that the Earth does that feeds back into that loop. However, for the sake of this talk, I'm not going to go into that, partially because it is not in my realm of knowledge, but also because I want to show you guys what it's like being a space weather analyst. So that brings me to our first topic, which are solar flares. So what is a solar flare? Well, a solar flare is, and I'm realizing it is not doing the animation that I thought it would, but that's okay. So solar flares are giant bursts of bright light, typically with solar radiation emitted from it. So we have a sudden brightening observed here over the limb of the solar disk, and it is usually interpreted by a large energy release. Many flares are followed by coronal mass ejections from the sun, which usually are seen as clouds of ejecta of electrons, ions, and atoms through the corona of the sun into space. And in this slide, as I mentioned, you can see a solar flare. And I meant to have this pop up so that it wasn't blocking the whole picture of the sun. But the good news is that you can see the solar flare here. And so with a solar flare on this limb, this is actually related to this bump in this flux. And so what we're looking at here is actually a timeline from a spacecraft in space called the GOES satellite. It is one of NOAA's satellites, and it is taking in data of the flux, the electron flux, or sorry, the X-ray flux of the sun, and telling us what the intensity levels are of it. And so what we can see here, what one I'm pointing out here, is actually related to this flare specifically, which is classified as an X1.5. But how does that classification work, right? So there's different classifications when we look at the sun. There are A class, B class, C class, M class, and X class flares. An A class flare would be your lowest values. So these would be from 10 to the -8 to 10 to the -7 values. Any flares that occur with the values in between 10 to the -7 to 10 to the -6 are considered B-class flares, which stand for background. 10 to the -6 to 10 to the -5 are considered C-class flares, which are considered common. And then we get into the higher flaring, which 10 to the -5 to 10 to the -4 are moderate class flares or M-class flares, and then we have 10 to the -4 to 10 to the -3, which are X-class flares, aka extreme. And so with this, we can see that this did reach the highest level. So it's kind of similar if you think about how they rate hurricanes and EF scale for tornadoes. So all of the scaling, we do have scaling in space weather as well, where we do A, B, C, M, and X for at least solar flares. And so I did mention solar flares are usually associated with coronal mass ejections, but they can occur often. They occur often without producing a CME, and CMEs can also occur without a solar flare. So if a solar flare isn't producing a coronal mass ejection or CME, excuse the jargon if I do bring that up, I'm going to try really hard to make sure I don't do too much jargon. So if you have a CME or a coronal mass ejection and it's not coming from a solar flare, what else could it come from? Well, we have filaments and prominences. So what's a filament or prominence? Well, they're one and the same. And when astronomers originally were looking at the sun, they thought that they were different. So when you look at these features, this is what we consider a filament or a prominence. And this one's actually really famous because it was a really nice view of an eruption. And this filament / prominence, so basically when it's called a prominence is typically when you see it along the limb of the sun. So you see it on the edges of the sun. And it's called a prominence because when they originally were looking at it, they thought they were different. When we see this material compared to the dark background of space, it looks bright. But as it rotates onto the disk, it ends up looking dark. So if you look at this image, which is actually from today, we can see some dark filament material here. You can see a little bit of filament material there. There's like kind of all of these dark little squiggly lines, and those are all filaments, but also prominences. And so we can see this also using the GOES spacecraft. And so we can see a little bit of that filament here, some filaments here. And so if we get an eruption from the sun with either a solar flare or a filament, we usually end up with a coronal mass ejection. However, I want to give you guys an idea of what the size scaling is of these filaments, because I feel like it's really hard to understand how large these are. And so looking at this guy, we're going to zoom in, and this is the Earth to scale. And so the Earth is very small in comparison to these huge eruptions that we get from the sun, just to give you an idea. And so when we get these eruptions, this is actually some pictures I overlaid together. We can get eruptions from the sun, like these filament eruptions can produce these coronal mass ejections, or CMEs. And so you're seeing a little bit of a glimpse of what these CMEs could look like. And so we're going to take a closer look at this one for a second. So you can see there's this eruption going on from the solar disk, and I actually lined it up so you can kind of see once it comes out of this field of view and goes into this field of view, you can kind of see where it maps out, and you can see that structure here, that really bright feature there. So my team that I work on, we will monitor the sun. We'll look to see what these eruptions look like, where are they going, and then we'll get an idea of, okay, if I'm seeing an eruption from here, where am I expecting to see it in a coronagraph, which we're going to show what those are in a second. Those are kind of covered here. And then I'm going to get an idea of this CME, or coronal mass ejection. I'm going to measure it and get an idea of where it's going. But I'm getting a little ahead of myself. So here is our CMEs. So we've got these beautiful coronal mass ejections, and what you can see here is that we're looking further out. So these are called coronagraphs, and these are both from the SOHO spacecraft, which I should have written down what SOHO stands for, but I know it's like Solar Observatory of some sort. I should have wrote it down. You use lingo all the time at work, and you just kind of forget what is not common knowledge. And so I apologize for that. But so these two are showing pictures of coronal mass ejections coming from the sun, which this is related again to this filament eruption that we had here. And so what we're seeing is that this basically is called an occulting disk. And if you saw the eclipses recently, what would happen during an eclipse is that this white circle is the sun, and the moon would cover that circle perfectly and in a total solar eclipse. With the annular solar eclipse, it didn't cover it fully, and so we had a little bit of a ring of fire around the sun, but we get full coverage. And so basically what we're seeing with coronagraphs is an artificial eclipse. And with these artificial eclipses, they're a bit further out in space. And so we're seeing more of the lower corona, or the sun's highest layer of the sun, covered, so that we can see these features that are typically too faint to see with how bright the solar disk is. And so we're blocking out all the brightness of the sun, and we're starting to see these beautiful large eruptions. And what we get here is called a light bulb CME. And so we call it a light bulb CME because we have this lovely leading edge, and then we've got this empty cavity, and then this little core in the middle. But basically it looks like a light bulb. And so there's many different types of coronal mass ejections, or CMEs, and some of my favorite, honestly, are these 3-part CMEs, these light bulb CMEs, because they're just the prettiest. But we will look at some other ones later. There's actually a little teaser of some activity that happened just before we started this. And so I will be showing you guys some of the real-time activity as if it was real-time, and what it's like to do space weather. So when we have a coronal mass ejection and a solar flare, typically what we end up seeing later on is the possibility of getting a solar energetic particle event. So what we can see here is a lot of channels. This is a lot of plots. So I do look at a lot of plots on the day-to-day as well. I don't get to just stare at images of the sun, but I do get to do that a lot as well. But once we have a solar flare, we'll have to look at these timelines to see, okay, is there any increases anywhere else? And so what we're seeing here is increases in the proton flux. And so I've got multiple channels here, and I kind of labeled it out, but this is through the GOES primary proton flux channels. And so this blue line here, this top line, this is the greater than 1 MeV channel. We've got the greater than 5 MeV channel in the black color. The cyan is greater than 10 MeV. The green is greater than 30 MeV. The orange is greater than 50 MeV. And then the red is greater than 100 MeV. And so you can see that depending on how strong an event is, it takes a minute for each thing to kind of jump up. So we had a nice solar flare, and this is actually related to the X-class flare I showed you that happened back on August 7th in the solar flare panel. And so we had that solar flare, and we did end up having a solar energetic particle event related to that. So what is a solar energetic particle event? Well, a solar energetic particle event is basically when we have this increased high energy protons impacting us at a faster pace. And so what we end up seeing is increased values. So usually we have, this is PFU, which stands for proton flux unit. And so we have 0.2 is usually kind of around where it stays at this background level. But once an event happens, we can see everything kind of skyrockets, and we start seeing elevated values. And so when it goes into a solar energetic proton event, we basically are crossing a threshold. And so that threshold, which was stated by NOAA's Space Weather Prediction Center of the 10 MeV for this greater than, so for the greater than 10 MeV channel is 10 PFU. So once it crosses this line, we basically are in a solar energetic particle event. And so you can see that we had 2 back-to-back solar energetic particle events, and it was a very busy week. So what else can we see from the sun? Well, this is actually an image from today. And so, because I really like this corona hole, it kind of looks like it's in the middle of a puzzle piece from the filaments around it. And so what we can see here is these very dark areas in the middle here. These dark regions, this is within the sun's solar corona. So the solar corona is the outermost layer of the sun, which is all this kind of like wispy, kind of like hair of the sun. And so basically this kind of hair of the sun, we get holes in them. So it's kind of, I guess, kind of like a bald spot if we're comparing it to hair. But what's happening here is we're having open magnetic field lines. Now, they're not truly open because physics would not allow that. But instead of the field lines connecting back to the sun, they actually go into the interplanetary space and connect elsewhere in the solar system. And so with this, typically what you'll have is you'll have open magnetic field lines connect to us here at Earth or to other places in interplanetary space. But as this coronal hole reaches longitudes closer to this side of the sun, we end up seeing some of this this increase in activity called a high-speed stream. And so a coronal hole high-speed stream is basically when the sun is allowing all of this open energy, this open flux comes from the sun, and this solar wind is much faster than the solar wind we normally see, which tends to be slower and more dense because the field lines aren't open to us. And so with this opening, we have dense, cooler regions that do allow us to have faster speeds. And so sometimes coronal holes and coronal mass ejections, as they arrive near Earth, we end up getting what are called geomagnetic storms. And so I'm kind of just walking you through all of the things that we, as a space weather analyst, we would look at and could be impacted by in order to do the job on the day-to-day. And so with the geomagnetic storm, what we will do is we'll be monitoring to see what the planetary K index looks like in the near Earth environment so that we can put out notifications related to what a geomagnetic storm is doing. And so this is all based off of the NOAA Space Weather Prediction Center, and I did grab an image from that of today's because I felt like my slide looked a little empty, but I am also sad that I covered up the really pretty aurora from the ISS. But with geomagnetic storms, most folks who look for a geomagnetic storm are looking for it in the sense of aurora, right? So they're looking, okay, when am I going to be able to see the aurora? And so this is where the KP comes in, and folks do sometimes use the KP, but if you're looking at arrival signatures in the near Earth environment, and we'll get to that, it's usually a bit easier to look at what the magnetic field is looking like at Earth. But I will show that in a bit. So we can see here what the categories are. So similarly to the flaring, we have categories of what the geomagnetic storms would be. So we have a G1 storm, which is a minor geomagnetic storm, goes to values of KP equaling 4.67 to KP equaling 5.33. We have a moderate geomagnetic storm, or a G2, which goes to KPs of 5.67 to 5.633, 6.33, and so on and so forth. So we have a strong geomagnetic storm, which is a G3, a severe geomagnetic storm, which is a G4, and an extreme geomagnetic storm, which is a G5. And so you'll notice here at the very bottom, the pattern kind of changes a little bit. And so a severe geomagnetic storm of KP values of 7.67 go actually up to KP values of 8.67, and extreme geomagnetic storming, or a G5, is related to KP values greater than or equal to 9. So a lot of lingo going on here. So what else do we look at? So if there's a geomagnetic storm, there likely was an arrival in the near Earth environment. And when we get a arrival in the near Earth environment, usually we'll end up getting a compression to the Earth's magnetic field. So the Earth is protecting us in this little safety bubble of a magnetic field, and that's magnetosphere. And when arrivals happen from the sun, we're well protected, but we do sometimes get a little bit of compression in our magnetic field due to this. And so what you're seeing here is something we look at called the modeled magnetopause standoff distance. And so the modeled magnetopause standoff distance can show you when there will be potentially a crossing into what we call geosynchronous orbit. And you may be wondering, okay, why would that be important to me? Well, this is important for all of our satellites. And so we end up seeing the possibility of changes to the upper layers of the Earth, so the ionosphere and whatnot, during these magnetopause crossings. And so we can have impacts to all of our satellites, which could end up being detrimental to the satellites. So it's important that satellites know, okay, what's happening with this. And so what you're seeing here is the time frame around here. So we're at like 14 Earth radii around here. And that you can see, this is what the magnetopause is in this model. And I'm not going to go through all of this, but you can see some of the spacecraft. So you've got the diamond here is related to where GOES 16 is. And the X here is related to where GOES 18 is. And you can see how far away our magnetopause is from this dashed line, which is geosynchronous orbit. And so during an event, we can see that this gets compressed, and we actually get a very minimal crossing. In this case, we have a very brief crossing into geosynchronous orbit. And so this is one of those times where we would let satellites that are related to NASA missions know, hey, there's a possibility of a magnetopause crossing based off of our models. Just so you know, like, take care of your satellites. So that leads me to impacts. So what kind of impacts you may see to satellites? And so we've gone all the way from the sun, what's happening at the sun, and we're going all the way to the impacts here near Earth. And basically, in an ever-growing technological world, space weather impacts us all. And some of my favorite ways this gets shown is one of my favorite people to listen to who talk about space weather is Tamitha Skov. If you don't know her, she's the Space Weather Woman, and I absolutely love her, but she does a really great job describing all of this and explaining what's going on in space weather in real time. And one of my favorite talks she gave was when she talked about the impacts of space weather during a hurricane. And so we had a hurricane that impacted Puerto Rico. I can't remember which hurricane it is off the top of my head, but I want to think it was, oh gosh, which hurricane was it? It doesn't matter. But there was a hurricane that impacted Puerto Rico. And at the same time of this hurricane, we had an arrival in the near Earth environment. And it actually impacted their ability to talk to ham radio operators and perform safety maneuvers to get folks out of there, because we were having, I think there was also a solar flare. There was a lot going on. And so basically there was all of this interference from space weather impacting their abilities to do efforts to do emergency management. And it's something you would never think of because maybe that's not applicable to you, but it is something that could impact people every day. As something maybe more closer home to you is if you have a cell phone and you're using your cell phone to get directions from your house to your work, and maybe it's your first time going to work. Well, if you are traveling during a solar storm, it's possible your GPS may start acting funny. It may not know where you are and whatnot, and that could just be due to interruptions from space. So I do love talking about all of these impacts and whatnot, but I would love to tell you about how space weather has impacted me personally and how I found myself in the space weather realm before I show you guys the coolest part of everything. So I'm going to talk a little bit more now about how I became a space weather analyst. So I grew up in Western Massachusetts, in a little town down in southwestern Massachusetts called Sandusfield. And so I grew up there with my family, and it was a completely dark sky area. So I was basically able to see the night sky all the time. I had no problem just enjoying looking at the night sky. And I gotta tell you, I will never ever take that for granted again now living in the DC metro area. But I absolutely love looking at the night sky, and I would just always look at the night sky. Anything that I could get my hands on related to the night sky, I would look at the night sky. And so as I went through high school, I would do extracurricular activities. I did things related to I did robotics, I did theater, I did all of these extra things, but my biggest dream was to do something in astronomy. I wanted to go to school to be an astronomer. And so when it came time to look into astronomy, my mom told me to look at, and if she's watching this, I love you, Mom. But my mom told me to look into what possible jobs there may be available in astronomy. And so we looked, and at the time, Google did not have the best search for potential jobs. And so I ended up only finding one job, and it was in Australia. And she was kind of like, maybe we should look at something else. And so I ended up looking into meteorology. And so I looked at I looked at atmospheric science as a major. And so I was looking at schools in the Northeast. And basically what ended up happening was there were only 4 schools in the Northeast that offered meteorology or atmospheric science as a major. And I knew for sure that I wanted to at least get out of Massachusetts. And so there was only 3 schools left after that. So there was one in Connecticut, there was one in New Hampshire, and then the one that I ended up choosing was in Vermont. And so Vermont became my second home, and I ended up going to Linden State College in northern Vermont. It was in the northeast corner. It was up here a little bit, and it's now known as Vermont State University at Linden. It's unified with a couple of the other schools in Vermont, but it was definitely my home away from home. And once again, it was in this beautiful area. There was beautiful night skies. I could see all of it. And I was studying meteorology, and I hated it. It was not for me. It was I was just not doing well with the meteorology. I loved the physics sides of things. I loved the math side of things. I could not stand doing the meteorological aspect of things, which is very ironic to me now. But during my years in doing atmospheric science, before I switched to doing applied math, I ended up looking at, I ended up going to conferences. So I went to the National American Meteorological Society meeting that my freshman year of college, and I found out about space weather, and it was the best decision I could have ever made to skip all of the other talks about tornadoes and hurricanes and go only to the space weather session, sit in there despite not having any background in space weather and just absorbing the information. And from that day on, I was hooked. I knew I wanted to do space weather. It was my dream. I could tell. I just was like, I got to learn more about this. I don't understand it yet, but I know this is where I'm going. And so I kind of let that passion fuel me. And during my years in college, I ended up doing 4 internships. 2 were technically research experiences for undergraduates, or REUs. And then I did 2 summer internships. So my first year, I ended up doing an internship with the National Solar Observatory in Sunspot, New Mexico. This was before they moved from Sunspot, New Mexico to Boulder, Colorado, and Hawaii. And so they used to have a location in Sunspot, New Mexico, which I love that it was called Sunspot. And then they had one in Tucson, Arizona. And so these were the 2 locations that they had their home bases. And I was at the Sunspot location, and I spent 12 weeks, which was crazy to me, but I spent 12 weeks out there doing my summer internship. And I wish I could tell people what the trick was to applying for that internship, but my trick was actually through networking. And networking has kind of been the best part of my journey. And so during my years in undergrad, my college put on what is called the Northeastern Storm Conference. And at the Northeastern Storm Conference, it's a student-led conference. It's one of the largest across, I believe, the states across the U.S. And this tiny little conference in the Northeast ended up introducing me to the president of NCAR or UCAR at the time. And basically, he mentioned space weather during his talk, his keynote speech. And I went up to him and I was like, hey, I'm really interested in space weather. I would love to learn more. Can you help me find out how to get internships? And he was like, do you have a business card? And I did not. And ever since then, I have kept business cards on me at all times because I am petrified of never having a business card at a moment that I need it. And so I ended up getting his card, and I wrote down my information on something else and I gave it to him. But I waited a week and I emailed him just to check in to see what I could possibly do to get an internship. And he ended up forwarding my email to all of these different agencies and folks that he knew to say, hey, this girl would like an internship. What can we do for her? And so he basically had helped me get an internship for that year. Now, mind you, this conference was in March, the beginning of March, and he got me a summer internship for that summer that started middle of May, which was insane to me. But I ended up getting this wonderful opportunity to get this internship. They had an open space. I ended up sending them all the information in order to be able to take the open space. And I spent a whole summer at the National Solar Observatory. I worked alongside some really fantastic solar physicists and learned so much, but it wasn't enough. And so I did an additional summer internship the year after that because I couldn't get this information at my undergrad. And so I knew that I needed to fill my gaps as much as I could during the summers. And so the next summer I applied to the Laboratory for Atmospheric and Space Physics in Boulder, Colorado, their summer REU program. And I ended up at Southwest Research Institute. And so at Southwest Research Institute, I ended up working alongside some of the well-known names in solar physics. I worked with Craig DeForest. I worked with Tim Howard and these folks ended up teaching me so much about solar physics. And I should mention at the NSO, I was with Han Eitenbrook, and he is so great, and he's always been a great mentor to me. And so I'm so thankful for these opportunities. But at Southwest Research Institute, my project involved slinkies. And so we looked at slinkies and tried to get an idea of what happens with how does a CME end up looking like that 3-part CME, that light bulb CME, if it doesn't have a filament. And so that inner part of that 3-part CME, that light bulb CME that I showed you, that's typically the core of it. That bright spot, the middle part, is typically called a filament in solar physics. And Tim Howard, who is my advisor, really wanted to dispute that. And so he really inspired me with solar physics, and we did a great research internship. And this one was only 8 weeks, but I was in Colorado. I was biking to and from my place I was staying into downtown Boulder with this giant backpack full of supplies to do my internship. And I ended up learning a lot about space weather and solar physics at that internship. And what ended up coming out of it was that I ended up getting to present my work at multiple locations. So at the National American Meteorological Society conference, at the American Geophysical Union conference, and I started networking even more. And so after that summer, I had the wonderful opportunity to also be part of a publication. And so I did end up getting to be a co-author on the publication regarding my summer internship work. And so I'm really happy that I had that chance, and it's just been really detrimental for me moving forward. And so now, closer to where I am now, I spent 2 summers here at NASA Goddard Space Flight Center. So the 2 summers after my summers at the National Solar Observatory and the Southwest Research Institute, I spent 2 summers here at Goddard, which I now call my home. And I got to work with even more brilliant solar physicists and some of the ionospheric physics folks. And it was just absolutely incredible. I did research on the ionosphere, which was totally out of my realm. And my supervisor was so helpful in making sure I knew exactly what I needed to do. And then my last summer internship was more in the realm of solar physics. And it was just all really wonderful. And so my first summer, I had worked with Katie Garcia Sage, who I love very much. And I then worked with Nikki Vile, who is brilliant and just incredible. And was a great mentor. And I am so excited that I get to work alongside both of them now. So beyond that, this is just kind of a collage of the images of where my life has taken me. And so in this picture, this is a picture from the Northeast Storm Conference, and that is Jim Cantori from the Weather Channel. He is an alum of my college, so we are both alums from there. This was from graduation day. This is actually with Liz McDonald from Aurorasaurus and Sarah Husil, who works at the 557th Weather Wing now. We were doing a little tour of Goddard before we got our jobs in the field. I attended Space Weather Workshop in Boulder, Colorado, and got to assist with planning it for the students, doing the student portion planning. And then this picture is from my last internship at the dressed as Miss Frizzle and talking about what I had learned from that summer internship. But my favorite part is this picture, which is actually from where I am now and in my job today. So now I want to use this as my little segue to talk about the Moon to Mars Space Weather Analysis Office. And so the Moon to Mars Space Weather Analysis Office is where I work currently. And this is their mission statement, but I am going to read it out for you guys. So the Moon to Mars Space Weather Analysis Office was established to support NASA's Space Radiation Analysis Group with human space exploration activities by providing novel capabilities to characterize the space radiation environment. M2M also supports NASA robotic missions and with space weather assessments and anomaly analysis support. the office will work as the proving grounds and test bed for capabilities that will eventually transition to operational agencies. So a lot of what I do on the day-to-day is specifically to help transition these this test bed of these capabilities to agencies such as the Space Weather Prediction Center. And so Space Weather Prediction Center, they're the official ones who give the forecast of space weather to the United States. They're the official government agency that does that. And so what we're kind of like the two in the operations to research pipeline. So we dabble our feet a little bit in the operation side and a little bit in the research side, but it's mostly to be that test bed so that we can help both sides get an idea of, okay, is this feasible in an operational environment? And so this is the team that I work on, and I wanted to make sure I got to point them out. But basically, we're a relatively small team right now, but we do huge things, great things, and so we would not be able to do as much as we do now. And I should mention that Tony is now officially out of training, and he is also a validation support person and analyst. And so you can see we're kind of all doing our own things. We've got anomaly support, we've got validation support, we support the James Webb Space Telescope, we do training within our team, which is a big task. We've got software development, we've got project management, and then of course outreach liaison is myself, and then my boss, who is the director and also does research on the side. And so with that, I want to show you guys. So we do a lot. These are just some, not all, of the groups we collaborate with. And so our big collaborators right now is the Community Coordinated Modeling Center, who helped us become who we are. The Space Radiation Analysis Group, who we support, and basically also helped create who we are. And then NOAA's Space Weather Prediction Center, which is technically part of the National Weather Service. We are really big collaborators with them, and they're fantastic. And honestly, I give them kudos all the time for all of the work that they have to do on the day-to-day. We work using this stereo spacecraft, so the Solar Terrestrial Relations Observatory. I'm realizing now that I didn't add SOHO's image in here. We've got the Solar Dynamics Observatory. We work with James Webb Space Telescope, with Parker Solar Probe, which is the mission to touch the sun. We work with Solar Orbiter, which its mission is trying to look closer to the polar caps of the sun, so the poles of the sun. The MAVEN mission and the Mars mission, both at Mars, so Mars, Perseverance, and Ingenuity. So Perseverance is the rover, Ingenuity is the helicopter. We've supported them. And then OSIRIS-REx, who just had their mission sample return of their asteroid, but the OSIRIS is continuing on and is now technically called OSIRIS-APEX. We're still assisting them. And then one of the big things that we support is the Artemis missions. And so with that, what does a normal day look like? So this is where I'm going to use it to kind of give you guys an idea of what a normal day looks like. And we're going to go and look at the real-time activity, because fun things have happened and I kind of want to show you guys. But shout out to Kat. Kat and I actually recently met at the annular eclipse, and we both were wearing sun outfits. My colleague sniped me eating out of a giant thing of goldfish. So this is kind of what a normal day looks like to me, is looking at the sun and then also in a meeting while eating. And then additionally going and doing outreach and doing presentations. And so this was a day of tutorials to a group in Argentina. And this was actually the week before I went to Texas for the annular eclipse. And so I was in Argentina getting to support all of that. And it was just a lot of fun. So with that, I want to really quickly hop on over to the imagery. So this is kind of closer to what I do on the day-to-day, and please feel free to let me know if you can or cannot see it. So we've got all of this imagery, and this is one of the Community Coordinated Modeling Center, or AKA CCMC's products, called ISWA, or the Integrated Space Weather Analysis. system. And so it allows you to kind of make your own layout, which is great. It's a lot of fun. But I wanted to show you guys, and I'm looking to see if everything loaded. This is basically what I get to do on the day-to-day. And so before this, just had an M-class flare, and it was a long duration M-class flare. And so what we're looking at in the bottom here, this is the Solar Dynamics Observatory. And over here, we've got the 131 angstroms, or 13.1 nanometer wavelength that we're looking at. And I want you guys to keep an eye out on this corner up here. And so basically what we end up seeing is we get this really nice flare and eruption. And so you can see that flaring there. And we can see it a little bit more in action here. We've got a really nice EUV wave, so an extreme ultraviolet wave in the corona. So that's the outer layer of the sun here. We can see that everything kind of waves through as that eruption goes by. And in other wavelengths, we can also see some of the eruption signatures, but I'm going to show in this wavelength, this is the 304 angstroms. This is what we typically use to look at the filaments and prominences. And so what you'll see here is this guy as part of that eruption. So we get that really nice filament eruption there. And then we can also see a little bit of that field line movement in the 171 angstroms. And so you're probably might be wondering, why is everything colored differently? And it's colored so that it's easier for us to look at this real quick and figure out, okay, which wavelength is related to which temperature of the sun, and also possibly know which angstrom we're looking at. So each one has a little key at the bottom of which it's displaying. So we've got the 131 angstroms, we've got 211 angstroms, 94 angstroms, 335 angstroms, the 193 angstroms, the 304 angstroms, and then the 171 angstroms. And each one can kind of show us a little bit different things of what's going on with this eruption. But the best part is probably the resulting coronal mass ejection from this. And so I'm going to show you guys. So activity's been on the low side recently, and we finally just had this nice kick up here tonight. And so we can see in the imagery here this really large CME. And so this large guy here is huge. And basically there's a bit of what's called a shock from it. So it was so powerful that there was a shock ahead of this bulk portion here, which is where the main mass of the CME is. And so we ended up, I did a quick measurement before this, and we can see that this guy, very preliminary, looks like it's going over 100 or over 1,000 kilometers per second. So it's a pretty fast CME of the imagery that we have so far. But this is, yeah, we can see that guy nice and large. So it's stretching from here all the way over to here. And so it's a big coronal mass ejection. But I think that was the main thing that I wanted to show. I'm happy to take questions. I can keep showing things. Sadly, we don't have more SOHO imagery yet. I think it's in a downlink. So, but that was the main stuff of what I wanted to show.
Carina, thank you so much. That was awesome. Now, really quickly, I have the exact same NASA socks. 2 pairs, in fact. And as a robotics girly who wanted to learn astronomy and then couldn't find any astronomy programs, your story really hit home for me.
I love that.
So we do have some questions and I just want to get to them here. So the first question I want to go ahead and Alexandra asks, could a CME fry the Earth to a crisp if it reached all the way to our planet?
So coronal mass ejections do end up impacting us here at Earth, and that's a great question. So I'm going into what's called the database of notifications, knowledge, and information, aka Donkey. We like our animals here. And so I'm just going to quickly pull up what's happened in the last week. And so if we go down and we look at some of this data, what you can see here is a bunch of simulations. And so these simulations here usually show us where a coronal mass ejection may be going. And so this is just a little simulation of a coronal mass ejection. This isn't the one of the CME that I was just showing, but basically what you're looking at here is the sun is in the middle. Earth is the yellow dot over here. We've got a bunch of NASA missions and planets all around here. So we've got Osiris Apex here. We've got the Stereo Ahead spacecraft just above us. We've got a new mission called Psyche back here, which just recently launched. We've got Venus over here. We've got Bepi Colombo, which is, I believe, an ESA mission. We've got Solar Orbiter, and then Parker Solar Probe down here, and then Mercury and Mars. But basically what you're seeing is just how the solar wind is moving. It's called a Parker spiral. But with that being said, long-winded answer, no. We will not get fried here. One of the biggest things you may have to worry about is like if we get an event that's really large, really strong, like considered Carrington size, which Carrington was an astronomer who basically saw a very intense solar flare and helped us learn more about sunspots and how the sun works a little bit from an early age, like 1859. But with a CME headed towards Earth, we're luckily in a protective bubble. So if we were to get any impacts, we have a pretty decent protective bubble, but there is the possibility that it could impact our electronics at some point. But it would take a really, 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 really strong storm to get to the point where it would negatively impact our electronics in a way. But if you want to learn more, the U.S. has an emergency management plan for if something like that were to happen. And so there's like a space weather emergency management plan that the government put together, and they do have plans of what could be available for that.
Awesome. Okay, so next question is from Stuart. How are CME's direction determined if it is aimed at the Earth given the time delay between ejecta and collision?
Ooh, that's a good question. So one of the things we do is we'll analyze CME. So you can see with this guy, what we do is basically we can play with, and I'll just reset this analysis. We have this tool called the SWPC CAT tool. So the Space Weather Prediction Center created this tool called the CAT tool, or CME analysis tool. And basically what it does is it lets us lasso the CME and figure out which direction it's going to go. But typically coronal mass ejections take 1 to 3 days to reach Earth. So you still have a decent amount of time to get a measurement of this before it impacts us here at Earth. And then if you're thinking about solar flares are different from coronal mass ejections. So solar flares would be that burst of radiation. And so the solar flare can cause a coronal mass ejection, but the solar flare itself usually takes like 20 to 8, I think it's like 20 minutes for the impacts from that solar flare itself to reach us. So that's usually when we start seeing those solar energetic particles.
And then once you identify and measure a CME, what do you do with the information?
Yeah, so once we identify CME, we analyze it, we will end up putting it into this database. So this is as I said, the Donkey database. And basically, if you go into search space weather activity, you can actually see what we've entered. And so if we have a solar flare, you can see we'll put in the solar flare, and then we'll put in the information related to that measurement of the CME. Now, not all CMEs, again, are associated with solar flares, but we can go in here and see where what that CME may have looked like. So we could see a CME back on October 21st that happened at 1342 Zulu, and see what the parameters were related to that CME. And you can actually click on it, get details of what the analysis was, see what they did for the analysis itself, and then if there's anything associated, there will be links to the activities here, so you'll see anything linked.
And now I know we spoke a little bit earlier when that data from SOHO came in about the Parker Solar Probe being very close to the sun right now. And so how are you able to prevent or avoid damage to a spacecraft like Parker since it's so close to the sun?
Yeah, so luckily for Parker, it was built to go into those things of the sun, so it's actually good it's going to be impacted. We want the data. We need Parker Solar Probe to get the data, but usually each mission will have their own set of rules of what they do. What we do for the missions is basically provide them as much information that they can use to do any safety protocols they may have for their instruments. So some may shut them down, put them in a safe mode or something like that, but it really depends on the mission and it depends on what they want.
And so now the next big question is, where can we follow the science? Where can we, what website or app is best to, look at the probability of seeing an aurora or studying that data?
Yeah, so there's a lot of good information out there. This is all open and available to the public. You're more than welcome to look at it. I would just say make sure you're reading everything in detail. Before posting, make sure you know what you're looking at. If you have questions, you're more than welcome to email me. I do have a little slide of details that I did not share. So I'll just put that up there if you want to email. Another place would be the Space Weather Live app, I think is what I have on my phone. The Space Weather Live app is fantastic, really good at alerting you about things. So highly recommend that. And then the Space Weather Prediction Center with NOAA, they're the official forecasters. So I would highly recommend looking at their stuff. They have things that they have a bunch of things you can subscribe to from them to get alerts as well. So.
All right, and we have time for just one more question before we wrap up. This is kind of a two-parter. So this is, Moon to Mars is what you focus on. And so will the future space travelers to Mars be able to protect themselves from solar radiation? And, can we talk about how space weather will impact humans in space, including those on the ISS?
Yeah, so that's a great question. We're doing as much as we can right now, and I think there's still a lot to learn. It would help if we had more satellites in space to get more ideas on what the radiation impacts are. But if you look up the Artemis 1 mission that NASA had last November, it was our wet dress rehearsal of what it'll look like to have humans on board the Orion spacecraft as it goes around the moon, because we're trying really hard to send folks at least back to the moon soon, like within the next year, and then eventually to Mars. And so it's a long journey to get there, but I think we're starting. We're in a good place of where we're starting. So, but there's definitely they've got. At least with Artemis 1, they had some protective vests on to see like what they could do of protecting folks against radiation dosages and whatnot, and then also some safety enclosures in the spacecraft and whatnot that'll just be to try and see what they can do.
Thank you. That was tremendous. So of course, everyone here can connect with Carina. Her information is on the slide here. And, thank you so much for spending your time with us here at Night Sky Network. And for our Zoom attendees, a survey will be posted to the chat. We always appreciate your feedback, comments, questions, suggestions, and you can find this webinar along with past webinars on the Night Sky Network YouTube channel. And then you can join us next month on Thursday, November 30th, where we'll hear from Dr. Travis Fisher on active galaxies, monsters of deep space, exploring the nature of active galaxies and the role they play in shaping the universe we see today.
Woohoo!
Thank you so much, everyone. So that's all for this evening. Keep looking up, and we will see you next month. Have a great night.
Thank you.
Take care.